Ni hao. Hello, everyone. My name is Samira Oliva Madrigal, and it is a pleasure to be here today at WAIFI 2022. Today, I will be presenting a collaborative effort with Dr. Soldamli, student Chen, student Yue, Dr. Jing, Dr. Wang, and Dr. Koch, and that is reduction-free multiplication for finite fields and polynomial rings. Now, I will be going over, what is the main problem that we are trying to solve, reduction techniques, the state of the art, and our starting point, how we developed our work, our test inputs, our hardware design, results, and applications. Now, to get started, what is the problem we are trying to solve? What is all this about? The main application. The problem we are trying to solve is fast multiplication with large numbers. In our case, we are working with operands that are elements over a finite field or ring and in the polynomial basis. So these are polynomials of large degree. And ideally, we would like to interleave multiplication and reduction. And not only that, but of course, obtain a significant speed up with respect to what is currently out there. And doing this, for fast multi-digit multipliers, such as, Schuhag, Strassen, or Fiora, is in general difficult. Now, as I mentioned, the main algebraic structures that we work with are finite fields of the form gf2 to the n and polynomial rings. And finite fields of the form gf2 to the n in particular for practicality, security, and efficiency reasons. Now, modular multiplication involves two steps, multiplication and reduction. And these can be done separately or interleaved into a single algorithm. All modular multipliers employ one type of reduction technique, even whether they do a Mastrovito matrix, whatever it is, but they employ some type of reduction. And with respect to the general ones, the beat parallel modular multipliers, they employ either left to right, right to left, or bipartite. Now, in this figure on the left side, we can see, an already computed product, and we reduce it from the most significant position, and an example of that would be Blakely. And in the middle figure, we see, the unique example of right to left reduction, which is Montgomery. And on the right side, we see interleaved multiplication and reduction. One part with Blakely and the other part with Montgomery. And these can be implemented as functional units that execute in parallel. And so this is a bipartite modular multiplier that was introduced by Kaihara and Takagi. Now, in 2015, Dr. Soldamli introduced a partially interleaved Karatsuba-ofman algorithm, modular multiplier. And this is a partially interleaved multiplier that combines Karatsuba-ofman multiplication with bipartite reduction, and only the first layer of Karatsuba-ofman, everything in a sequential fashion. And as you know, Karatsuba-ofman is a recursive divide and conquer algorithm that allows us to compute the product of the 2-digit numbers, using 3 multiplications as opposed to 4 multiplications. And in the case where we are working with rather large numbers, we split them in half size, and depending on the the base we are working with, if we adopt it to GF2 to the n, other requirements, and compute in a recursive manner until we reach a single digit or single bit. But of course, the level, how deep we go into the recursion depends on what we want, what we are working with. Now, our starting point was a naive implementation of FIKO, where we compute the Karatsuba terms, then we do the quotients, Montgomery and the standard quotients, then we compute the bipartite reduction and the reduction terms and our final sum. And here we see a simplified finite state machine of that, and on the left, more explicit view of the terms for FIKO. And this this was not a very efficient, of course. What else? How can we improve it? And of course, the next step would be let's do interleaved multiplication and reduction, and we reduce one state from the FSM, and so we compute, the quotients. We do interleaved multiplication and reduction when we compute the Karatsuba terms, so we get the quotients and those terms in RCC, and then our bipartite terms and reduced terms. And now our next step is, how can we do all of this, together? And so before we get into that, I will discuss the parameters. So for FIKO, fully interleaved Karatsuba-ofman and reduction-free FIKO, we work with prefixed operands because of the nature of the modulus polynomial. We prefix the operands to have equal length for symmetry, and for our purposes, we work with a trinomial that is necessarily of odd degree so that we can split it evenly. And we use the term k-bit curve to describe, the modulus polynomial as a curve with respect to the degree. So if it is using an ECDSA odd curve. And we work with half size registers of size RSK over 2. Now, so our first goal was to have a fully interleaved Karatsuba-ofman algorithm, develop that then into a reduction-free, and get something that is significant, get some speed up at least over bipartite. The first goal, how do we take the most recent work and make it fully interleaved, where we have a bit parallel implementation, and we are computing 1 bit of each term in parallel per clock cycle. And of course, what the main problem here would be the quotients, right? That's the main thing that pops out. How do we do that? Because we compute the quotients from opposite directions. So the first point to address is, computing the products from either direction. Yes, we can do that correctly, we know that. But can we compute the quotients without any dependencies? And yes, we can. And we can easily see this if we consider, for example, a small field of GF2 to the 9, and we consider the product of 2 upper words, 2 upper registers. And we know because we prefix them, for example, such words would have the product of these would have a maximum degree of 6, and the upper bits would always be 0. And so, yes, we can compute the product correctly from that direction, from the most significant position. And similarly, we can also compute the quotient. And if we do it bit by bit, we can see that there are no dependencies. First, for the most significant bits, we never do this shift because we know that value will always be 0. And for subsequent ones, we know that the amount by which we shift one of the operands becomes fixed, and so we can take the quotient bits, the subsequent quotient bits without any dependencies. And so we can have, a fully interleaved Karatsuba-ofman. And so we can compute a residue in RCC. Now, with respect to time and the space, this is kind of similar to thing is being computed in RCC, but the space, and so from this, how can we develop a reduction-free version, clearly we must somehow be able to get rid of the bipartite circuit. And, this implies necessarily that there's some sort of interesting arithmetic that allows us to do this. We must be able to get something for free. And yes, indeed, that is the case when the modulus polynomial has a particular form. Now, ideally, we would like it to be, a binomial, but we're working, this with a trinomial for our purposes and of necessarily odd prime degree. And so if we can have a trinomial that we can split in such a form, because we're working with half-size words, for the fully interleaved Karatsuba-ofman with bipartite reduction, we can see that, okay, for Montgomery, we can easily see that, anything, any half-size words that is reduced modulo 1, the quotient is always going to be that value. For Blakely, it may not be quite obvious, but if we compute and we observe the terms, we can see that, the quotients are actually in the Karatsuba terms. For Montgomery, it's not so hard to see. For the Blakely quotient, it requires a little bit more observation, but we can clearly see that, yes, we have the quotients there. And this is a fully worked example of, how we get those quotients. And so we can remove the reduction circuit. So in here, in the state 2, this is where all our work is being done. So we just compute our multiplications. We can compute our 3 Karatsuba terms. And so we can obtain a residue in exactly RCC with just, 3 distinct multiplications and, some shifts and additions. And so in the last, at the last clock cycle, at the end, we can compute just, we got our quotients for free, and everything else can be implemented as just some shifts and additions, because for fixed, for known power, when, for F1, for example, we know that we can implement multiplication by known powers of 2 as shifts and additions. So we can do that in the last in the last clock cycle. Now this is our test input. Work with these trinomials that you have seen before, the last 2, and this is our special trinomial. That has that the lower word is 1 and the upper word is a binomial of this form. And we work with ECDSA curves and Mersenne primes. And for each trinomial, we define separate groups for the set of curves. So F2 would define a group of finite fields for all the ECDSA curves or exponents where the defining polynomial is an RFT. And this is the register transfer level design for RF-FIKO. And as you can see, it's pretty straightforward. We have just the 3 distinct multiplications. The rest, everything is just shifts and additions. It's just a first state, more FSM, and we implemented vertex 7 FPGA and HDL to ASIC design using TSMC 28 nanometer CMOS technology. And the results, it's what we expected. We accomplished our goal. We not only did better than, we obtained some speed up compared to BMM, but we completely removed the reduction circuit. So this is a truly reduction-free modular multiplier that is fully interleaved. And in particular for curves GF2 to the 107, GF2 to the 163, FIKO is more efficient than BMM, and for non-RFT curves, BMM and FIKO behave similar. RF-FIKO, is slightly faster than FIKO and BMM at approximately half the loop count for GF2 to the 107 curve, and faster, a little bit faster for 2 to the 163 compared to FIKO and BMM. And now with comparison to the fastest speed parallel modular multipliers in general, there's notable savings with respect to space complexity, and similar theoretically for the time. Here we can see, RF-FIKO for GF2 to the 107, 163, compared to the others, particularly BMM, it has approximately half the load count and, slightly faster, and similar for, 163, and not quite so for the others. This is just for the last two. These are non-RFT groups, and so we don't include RF-FIKO in there. And this is a more clear graphical representation where you can see RF-FIKO for those two particular curves. ASIC, the results were similar, except of course faster. RF-FIKO, slightly faster than BMM, and the area times time metric, it's less, and similar for 2 to the 163. And again, for the same curves, basic results. And now with comparison to some of the fastest speed parallel modular multipliers in the polynomial basis, if we take RF-FIKO for GF2 to the 163, it uses 6 times less gates than some of these, and 4 times less gates than the one by Lee et al. And of course, we can estimate the time delay as a function of the signal propagation through all the AND and XOR gates, to follow something similar. Applications, clearly ECDSA and RSA, lattice-based schemes where the polynomial ring for Q a power of 2, it's applicable to cases where, entity is ring friendly, and even cases where it's unfriendly, we would apply it, because entity is not always applicable in the case, for example, of compression, using compression with Saber. And even in the general case, whenever we can express Q in a form that we can apply RFT in GF2 to the N, we can apply it. So we can get rid of reduction completely in the NTT. So NTT takes care of reduction with respect to the modulus, but there's still reduction left with respect to the coefficients when they are defined over Z. And so in this case, RF-FIKO can get rid of that. And now, of course, a fully homomorphic encryption, where the functions work with modulus polynomials of rather much larger degree than in the post-quantum cryptography cases, schemes. And, these are some estimates for FHE for, in comparison, like if we consider RF-FIKO for like a 163 curve, what would be approximately the gate count? And we can see, it's pretty good. And these are some of the rings that are used in the PQC schemes, table 4. Now, conclusion, RF-FIKO completely removes bipartite reduction. We obtain a residue in just 3 distinct multiplications with some shifts and additions in the last clock cycle, at the end of the last clock cycle. And, we meet constant time requirements. There's no leakage with respect to modular reduction because there is none. And, we compute the residue strictly as a function of the bit length of the curve. So for k-bit curves, k over 2cc. We estimate, notable improvement with respect to space. And we compared, with some of the fastest ones for GF2 to the 147. There was a notable improvement. And of course, we expect the same with respect to time. And our conclusion is that, this was just a straightforward implementation, and there are clearly many other ways in which it can be improved. and incorporate it with other techniques. And we believe that it merits further studies. And thank you so much for your time.